Here's something that should bother you more than it does. A Boeing 777 weighs over 350 tons at landing. It's descending at 250 kilometers per hour, and in a fraction of a second, 6 rubber tires slam into concrete, go from 0 to full rotational speed, and absorb the impact of a small building falling from the sky. Normal car tires would vaporize, literally explode into fragments. So why don't airplane tires? The answer isn't just stronger rubber, it's a completely different engineering philosophy. And once you understand it, you'll realize that airplane tires are one of the most underappreciated technologies, keeping you alive at 40,000 feet. Let's frame the problem properly. When you drive your car at highway speed, your tires handle maybe 500 kilograms of load each. They rotate a few hundred times per minute. The rubber heats up slightly, wears down gradually, and lasts tens of thousands of kilometers. Now imagine this. A commercial airliner lands with a total weight of 300 tons. That weight is distributed across perhaps 12 to 18 tires depending on the aircraft. Each tire must handle loads between 20 and 30 tons. At touchdown, the aircraft is moving at roughly 270 kilometers per hour. The tires are stationary. In approximately 0.2 seconds, they must spin up from 0 to over 1,400 revolutions per minute. That's not gradual wear. That's controlled violence. The rubber surface doesn't just heat up. It can reach temperatures exceeding 200 degrees Celsius in that first second of contact. The friction is so intense that you can see smoke rising from the runway, and yet somehow the tires survive. They don't burst. They don't shred. They land the same aircraft dozens, sometimes hundreds of times before replacement. How is that possible? Let's put some real numbers on this. A typical main landing gear tire on a Boeing 737 is rated for loads up to 22 tons. That's one tire. The aircraft has 4 main gear tires plus 2 nose gear tires. Each main tire is inflated to approximately 200 psi. For comparison, your car tires run at about 32 psi. That's over 6 times the pressure. But here's where it gets more interesting. That same tire is designed to operate at speeds up to 378 kilometers per hour. It must survive repeated cycles of heating and cooling. It must function reliably at temperatures ranging from minus 55 degrees Celsius at cruising altitude to over 60 degrees on a hot tarmac. And it must maintain structural integrity, even if a portion of its tread is damaged. The certification requirements are extreme. Aircraft tires must pass what's called a dynamometer test. The tire is mounted on a massive rotating drum and subjected to loads 20% higher than maximum rated capacity. It must complete multiple cycles without failure. Then it's subjected to overspeed tests, exceeding maximum rated speed by significant margins. If it survives all of that, it can be certified for use. And even then, the tire you fly on has typically been recapped and reused multiple times before you ever board the aircraft. Most people assume airplane tires are just bigger, thicker car tires. That's completely wrong. An automotive tire is designed for comfort, fuel efficiency, and longevity over distance. It has a complex tread pattern to channel water and provide grip in various conditions. It's optimized for sustained rolling with minimal heat buildup. An aircraft tire is designed for one thing: surviving extreme short-duration stress. There's no complex tread pattern. If you look at an aircraft tire, you'll notice the grooves are minimal. That's intentional. Complex tread patterns create stress concentration points. Under the loads aircraft tires experience, those points would become failure zones. Aircraft tires don't need to channel water the same way car tires do. The landing speeds are so high that hydroplaning dynamics are different. Runway surfaces are engineered with specific textures and drainage to work with aircraft tire design, not against it. And here's another difference most people miss. Car tires are tubeless. Aircraft tires use inner tubes. Why? Because if a tubeless tire develops a slow leak at 40,000 feet, you won't notice until landing. An inner tube creates a more predictable failure mode. You can inspect it. You can detect pressure loss. You can replace it independently of the outer tire. It's not about being primitive. It's about being inspectable. So what makes an aircraft tire actually work? Let me break it down into 3 core elements. First, the carcass structure. The carcass is the internal skeleton of the tire. In aircraft tires, this isn't just rubber. It's layers of nylon or aramid fabric bonded together in precise orientations. Some tires use bias ply construction, where the fabric layers cross diagonally. Others use radial construction, where they run perpendicular to the direction of travel. The key is redundancy. Each layer provides backup for the others. If one layer develops a weakness, the adjacent layers carry the load. This distributed strength is what allows the tire to handle impact forces that would tear a single-layer structure apart. Second, the rubber compound. Aircraft tire rubber is not the same formulation as automotive rubber. It's engineered for entirely different priorities. The compound must remain flexible at extremely cold temperatures. At cruising altitude, the tire cools to temperatures that would make standard rubber brittle and crack-prone. Yet moments later, during landing, that same rubber must withstand surface temperatures exceeding 200 degrees Celsius without losing structural integrity or becoming too soft. This requires specialized polymer chemistry. The exact formulations are proprietary, but they typically include heat-resistant elastomers, reinforcing fillers, and stabilizers that prevent breakdown under repeated thermal cycling. Third, the bead structure. The bead is where the tire meets the wheel rim. In a car tire, this connection handles modest forces. In an aircraft tire, the bead must resist forces that could tear the tire right off the wheel. Aircraft tire beads typically use multiple steel cable bundles wrapped in rubber. The design ensures that even under extreme deceleration and side loading during landing, the tire cannot unseat from the rim. A tire detaching during landing would be catastrophic. The bead is engineered to make that virtually impossible. Now let's go one level deeper into what happens during that critical touchdown moment. When the aircraft touches down, the tires aren't spinning, they're stationary. The runway is moving beneath them at 270 kilometers per hour. What happens next is controlled skidding. For a fraction of a second, the tire rubber slides against the concrete. This is the moment of maximum stress. The friction generates enormous heat. The rubber surface can reach its glass transition temperature, where it briefly becomes almost plastic-like before the tire spins up and the sliding stops. Aircraft tires are designed to survive this transition. The rubber compound is formulated so that this brief semi-plastic state doesn't cause catastrophic failure. Instead, the surface layer sacrifices itself slightly. You can see this as the puff of smoke on landing. That smoke is tiny rubber particles being ablated off the tire surface. This is not damage. This is designed behavior. The tire loses perhaps a fraction of a millimeter of rubber each landing. That loss is accounted for in the tire's rated lifespan. A typical aircraft tire is certified for somewhere between 200 and 500 landings, depending on aircraft weight and operating conditions. And here's where nitrogen inflation comes in. Aircraft tires are filled with nitrogen, not air. There are two reasons for this. First, nitrogen is more stable under temperature changes. As the tire heats during landing and cools at altitude, nitrogen maintains more consistent pressure than air would. This predictability is critical for landing gear system design. Second, and more importantly, nitrogen doesn't support combustion. If you filled a tire with regular air and it heated to extreme temperatures, the oxygen in the air could potentially contribute to an internal fire if the tire structure was compromised. Nitrogen eliminates that risk. It's not exotic technology. It's practical risk elimination. Let's talk about how this plays out in actual operations. Aircraft tires are not single-use items. They're designed for retreading. When the tread wears down, the tire is removed, inspected, and if the carcass is still sound, it's sent for retreading. New rubber is applied. The tire is recertified, and it goes back into service. A single tire carcass can typically be retreaded 6 to 8 times before it's retired. This isn't cutting corners, it's by design. The carcass structure is engineered to outlast multiple tread layers. This retreading system has significant economic impact. A new aircraft tire can cost anywhere from $1,000 to over $5,000 depending on size and rating. Retreading costs a fraction of that. For airlines operating hundreds of aircraft, each making thousands of landings per year, the savings are substantial. But retreading only works if inspection is rigorous. Every tire that comes off an aircraft is inspected for damage. The carcass is checked for internal defects using specialized equipment. Any tire that shows signs of structural compromise is retired permanently. This inspection protocol is why aircraft tire failures are extremely rare despite the extreme conditions they operate in. But tires do fail. Let's talk about when and why. The most common failure mode isn't explosion, it's deflation. Debris on the runway can puncture tires. Metal fragments, broken concrete, even bird strike remains can damage the rubber surface. In most cases, the tire deflates gradually rather than bursting. The multi-layer carcass structure prevents catastrophic rupture. Aircraft are designed to handle this. Landing gear systems are redundant. If one tire deflates, the adjacent tires take the load. Pilots are trained for rejected takeoffs with tire failure. Runways have emergency stopping systems, but there are edge cases if multiple tires fail simultaneously. If the aircraft lands significantly overweight, if braking generates extreme heat beyond design limits, the situation becomes serious. Brake fires can spread to tires. Overheated tires can eventually fail. This is why aircraft have brake temperature monitoring systems. Pilots can see brake temperatures in real time. After a hard landing or heavy braking, the aircraft may be required to stop and wait for brakes to cool before taxiing further. Taking off with overheated brakes and tires is not permitted. The system has redundancy, but the redundancy requires procedural discipline. So let's return to the original question. Why don't airplane tires explode on landing? The answer is everything we've discussed working together. The multi-layer carcass provides distributed strength. The specialized rubber compound survives extreme thermal cycling. The bead structure locks the tire to the rim under any force. The nitrogen inflation eliminates combustion risk. The designed ablation during touchdown sacrifices surface rubber to protect structural integrity. It's not one technology, it's a system. And that system is so reliable that most passengers never think about it. You board the aircraft, you land, you walk off. The tires did their job. They'll do it again tomorrow and the day after for hundreds of cycles. That's not luck. That's engineering. There's actually another part of landing that's equally fascinating. You've probably noticed that aircraft tires produce that puff of smoke on touchdown. Ever wondered if there's a way to eliminate that? Some engineers have tried. They've designed wheels that spin the tires up before landing. The results were surprising, but that's a topic for another video.